What if I told you that light never actually moves through space? Everything you believe about motion, distance, and even reality at least could be wrong. Because what I discovered isn't just strange, it flips your understanding of the universe upside down. And once you see it, you can't unsee it. Here's where reality begins to crack. We imagine space as an empty container, like a giant box, and light as something flying through it. But what if space isn't a container at all? What if it's more like a fabric, or even more radically, a network of relationships? In that case, light isn't moving through space. It's updating the state of the universe itself. Think of it like this, not a runner crossing a field, but a ripple that is the field changing. So when we say light travels, we might just be using language that's too crude for what's actually happening. Before we go further, I want you to pause and think, if light doesn't move the way we think, then what else in your life feels real, but might just be an illusion of perspective? Hold on to that thought, because what comes next gets even stranger and the most unsettling part. You're not watching light travel to your eyes right now. You're witnessing reality update itself in real time. The first idea, that light does not require a medium, yet still challenges our intuition of movement. Sounds simple at first, but it quietly dismantles one of the most deeply rooted assumptions we have about reality. Every experience you've ever had with motion involves something moving through something else. A car moves through air. A swimmer moves through water. Sound moves through vibrations in matter. In all these cases, there is a background, a medium that carries the motion. So naturally, when people first tried to understand light, they assumed it must also travel through some invisible substance filling space. This hypothetical medium was called that supposedly allowed light waves to propagate, much like air allows sound to travel. But here's where things start to break. Experiments, most famously the Michelson-Morley experiment, were designed to detect this medium. If Earth was moving through this ether, then light should behave differently depending on direction, like a swimmer going with or against a current. Yet no such difference was ever found. The results were not just surprising, they were devastating to the idea of a medium. Light behaved as if there was nothing there at all. No resistance, no background flow, no detectable substance guiding it. So physics made a radical shift. Light does not need a medium. It propagates through what we call empty space. But this creates a deeper problem than it solves, because now we are left with a form of motion that has no reference substance. When something moves without a medium, what exactly is it moving through? What defines its motion? This is where intuition starts to fail. Without a medium, the concept of movement becomes abstract. We rely on coordinates, distances, and time intervals to describe how light changes position, but those are constructs, ways of measuring, not necessarily reflections of what is fundamentally happening. In other words, we describe light as moving because we observe changes in position over time, but that doesn't mean it moves in the same physical sense as objects interacting with a medium. The discomfort deepens when you consider how uniquely light behaves compared to everything else. Its speed is always the same, regardless of the motion of the observer or the source. This was formalized in special relativity, which forces us to abandon the idea that space and time are fixed backgrounds. Instead, they adjust themselves to ensure that light speed remains constant. Think about that. Rather than light adapting to space and time adapt to light. So now the picture becomes even stranger. Light doesn't move through a medium, and it doesn't behave relative to a fixed background. Instead, the very framework we use to describe motion bends around it. This suggests that what we call movement might not be an inherent property of light itself, but a feature of how we observe and measure changes in the universe. At this point, it's worth questioning the language we use. Saying light travels through space may be convenient, but it might also be misleading. It implies a classical journey, something going from one place to another over time within a pre-existing stage. But without a medium and without absolute space and time, that stage may not exist in the way we imagine. What remains is a pattern of change, an event at one point linked to an event at another. So instead of thinking of light as an object moving through emptiness, it may be more accurate to think of it as a process, something that connects points in the universe without relying on a background substance. And that subtle shift from object in motion to relationship in change is where our everyday understanding of reality begins to unravel. The idea that the speed of light is always constant, no matter who measures it or how they are moving, seems innocent at first, but it quietly overturns the entire structure of how we understand motion. In everyday life, speeds add and subtract in intuitive ways. If you throw a ball forward while sitting in a moving car, someone standing on the road will measure the ball speed as the speed of the car plus the speed of the throw. This simple addition of velocities feels obvious because it works for nearly everything we experience, but light refuses to obey this rule. No matter how fast you move, whether you are standing still, running, flying in a jet, or even traveling at a significant fraction of light speed itself, if you measure a beam of light, you will always get the same value, approximately 299,792 kilometers per second. This is not an approximation due to measurement error. It is a fundamental property of reality. The constancy of light speed was firmly established through experiments like the Michelson-Morley experiment, which showed that light's behavior does not depend on Earth's motion through space. Later, this strange result became the cornerstone of special relativity. But here's where things become deeply unsettling. If the speed of light cannot change, then something else must give. When velocities don't add the way we expect, the universe compensates by altering space and time themselves. Distances contract and time dilates, depending on the relative motion between observers. These are not illusions or measurement errors. They are real physical effects. A clock moving relative to you will tick more slowly, and lengths along the direction of motion will shrink. This means that two observers moving differently through space will disagree about how much time has passed or how long an object is, yet both will measure the same speed of light. This completely breaks the classical idea that space and time are absolute. In the old view, space was a fixed stage and time flowed uniformly for everyone. Motion happened within this rigid framework, but the constancy of light speed forces a new picture. Space and time are flexible, interwoven, and dependent on the observer. They are not the background, they are part of the dynamics. Now consider what this implies about motion itself. If measuring motion requires space and time themselves shift depending on the observer, then motion is no longer an objective, universal fact. It becomes relational. Light's constant speed acts like a kind of anchor, forcing all observers to adjust their measurements so that this one rule is never violated. Instead of light adapting to the universe adapts to light. This leads to a subtle but profound realization. When we say light moves at a constant speed, we are not just describing light. We are defining the structure of reality. The speed of light is not simply a property of a particle or a wave. It is a built-in feature of space-time itself. It sets the maximum speed at which any information or influence can travel, shaping causality and the order of events. But there is an even deeper layer. If all observers, regardless of their motion, measure the same speed of light, then there is no privileged frame of reference. No one can claim to be truly at rest or in motion in any absolute sense. Everything is relative except for this one invariant, the speed of light. It becomes the only universal standard, replacing the idea of absolute space and absolute time. And this is where intuition begins to collapse, because we are left with a universe where motion does not behave the way we think it should, where time can stretch and compress, where distances can shrink, and where the only thing that remains fixed is something that itself defies ordinary understanding. The constancy of light's speed is not just a curious fact, it is a constraint that reshapes reality at its core, forcing us to abandon the comfortable notion that movement is simply about objects changing position in a stable, unchanging world. The idea that space itself may not be an empty stage but an active participant forces a complete rethinking of what we mean by reality. In everyday thinking, space is treated like a passive container, a kind of invisible box where everything happens. Objects move inside it, forces act within it, and events unfold across it. But space itself does nothing. It simply is. This assumption feels natural because it aligns with how we perceive the world. Distance seems fixed, directions seem stable, and space appears unaffected by what occurs within it. But this picture begins to break down when we examine gravity more closely. In classical physics, gravity was understood as a force acting at a distance, pulling objects toward one another through empty space. However, this explanation leaves a gap. How does the force travel? What carries it? The answer that emerged in general relativity was radical. Gravity is not a force moving through space. Instead, it is the result of space itself being curved and deformed by mass and energy. Imagine placing a heavy object on a stretched fabric. The fabric bends and smaller objects placed nearby roll toward it, not because they are being pulled by an invisible force, but because the surface they are on is no longer flat. This analogy, while simplified, captures the essence of the idea. Space is not passive. It reacts, it changes shape, it influences how objects move, not by pushing or pulling them in the traditional sense, but by defining the paths they can take. This means that what we interpret as motion under gravity is actually objects following the natural geometry of space. Planets orbit stars not because they are being actively pulled, but because they are moving along curved paths in a warped space-time. Light itself, which we often think of as traveling in straight lines, bends when it passes near massive objects. This phenomenon, known as gravitational lensing, shows that even light cannot ignore the structure of space. It doesn't resist the curvature, it follows it. At this point, the concept of space as an empty void becomes impossible to maintain. Space has properties. It can stretch, compress, ripple, and curve. In fact, disturbances in this structure propagate as waves, gravitational waves, detected in events like the first detection of gravitational waves. These waves are not traveling through space in the traditional sense. They are vibrations of space itself. The medium and the motion are the same thing. Now consider the implication for light. If space is dynamic and responsive, then light is not simply moving through a neutral background. Its path, its behavior, and even the way we measure its motion are shaped by the structure of space at every point. This suggests that light's movement may actually be inseparable from the geometry it inhabits. Instead of picturing a photon as a tiny object flying across an empty void, it may be more accurate to think of it as something whose existence is intertwined with the state of space-time. This shifts the entire framework of understanding. Motion is no longer about objects traveling through a fixed stage. It becomes a story about how entities interact with a dynamic, evolving structure. Space is not just where things happen. It is part of what is happening. It responds to energy, guides motion, and participates in every physical process. And this participation runs deeper than gravity alone. Quantum theories suggest that even what we call empty space is filled with fluctuations, temporary changes in energy that appear and disappear spontaneously. This hints that space is not just dynamic on large scales, but also active at the smallest levels imaginable. It is not a void, but a restless, ever-changing entity. When you put all of this together, the original assumption that light moves through space like a traveler through a landscape starts to feel incomplete. If the landscape itself is shifting, bending, and interacting with what moves across it, then the distinction between the traveler and the path begins to blur. Light does not simply pass through space, it exists within a system where space itself is constantly shaping and being shaped. The statement that photons experience no time is one of the most counterintuitive consequences of modern physics, and it directly challenges the way we understand motion, journeys, and even existence itself. To begin unpacking this, consider what it means to experience time. For any object with mass, like a human, a planet, or even a fast-moving spaceship, time passes along its path. This passage of time can vary depending on speed and gravity, but it never stops completely. There is always a sequence of moments, a before and an after, a duration that defines the object's journey. However, when we examine light within the framework of special relativity, something extraordinary happens. As an object's speed approaches the speed of light, time for that object slows down relative to an outside observer. This effect, known as time dilation, becomes more extreme the faster the object moves. At everyday speeds, the difference is negligible, but at velocities close to the speed of light, time can slow dramatically. Now take this idea to its ultimate limit. What happens at the exact speed of light? According to the equations of relativity, time dilation becomes infinite at that limit. From the perspective of a photon, a particle of light, no time passes at all between its emission and its absorption. This is not a poetic statement. It is a direct implication of the mathematics. If a photon could have a point of view, it would not perceive a journey through space. Instead, the event of its creation and the event of its arrival would be effectively the same moment. This leads to a deeply unsettling conclusion. From our perspective, light can travel vast distances. A photon emitted by the sun takes about 8 minutes to reach Earth. A photon from a distant galaxy might take millions or even billions of years to arrive. We interpret this as a day-long journey through space over time. But from the photon's perspective, there is no duration, no passage of time, no sense of distance being covered. The entire path collapses into a single timeless connection between two events. At this point, the notion of movement begins to unravel. Movement, as we understand it, requires time. An object changes position as time progresses. But if there is no time, then there is no process of moving from one place to another. There is only a relationship between where something begins and where it ends. For light, the concept of a path may be more of a description we impose rather than something physically experienced. This also forces us to rethink distance. Distance is typically defined as how far something travels over time. But if time does not pass for light, what does distance mean in that context? From our frame of reference, distance is very real and measurable. But for the photon, the separation between 2 points does not exist in the same way. The beginning and the end are directly connected without any experienced interval. The implications extend even further. If light connects events without experiencing time, then it acts less like a traveling object and more like a bridge between points in space-time. It links cause and effect without undergoing the journey we imagine. This perspective aligns with the idea that the universe is not fundamentally built from objects moving through space over time, but from relationships between events. Light becomes the mechanism that defines these relationships, enforcing the structure of causality while remaining outside the flow of time itself. This does not mean that light literally ignores time in every sense. From our perspective as observers, time clearly passes as light travels. We can measure its speed, calculate its travel time, and observe its motion. But this is a feature of our frame of reference, not of the photon's own experience. The key insight is that different observers can have fundamentally different descriptions of the same phenomenon, and both can be valid within their respective frames. So when we say that photons experience no time, we are not just making an abstract claim. We are pointing to a fundamental mismatch between how reality appears to us and how it behaves at its most basic level. The idea of a journey, of something moving step by step through space, may be a limitation of our perspective rather than a true reflection of what is happening for light itself. The idea that what we call movement might actually be a change in relationships rather than a change in position sounds abstract at first, but it cuts directly into the foundation of how we interpret reality. In everyday thinking, movement is simple. An object exists at one point in space, then later at another, and the difference between those positions defines motion. This assumes that space is a fixed grid, like a coordinate system laid out independently of everything else, and objects move across that grid as time passes. It feels obvious because it matches how we measure things, how we navigate, and how we describe events. But when you look deeper into modern physics, that picture starts to dissolve. The coordinates we use, x, y, z, and time, are not things that exist independently in nature. They are tools we impose to describe relationships between events. When we say an object has moved, what we are really saying is that its relationship to other objects has changed. Its distance from something else is different. Its configuration relative to the rest of the universe has shifted. Without other reference points, the idea of position itself becomes meaningless. This becomes clearer when considering relativity. In special relativity, there is no absolute frame of reference. There is no universal grid that defines where things are. Instead, every measurement of position and motion depends on the observer's frame. Two observers moving relative to each other will disagree on distances, times, and even whether two events happen simultaneously. Yet both descriptions are equally valid. This tells us that position is not an intrinsic property of an object, it is a relational one. If position is relational, then movement, being a change in position, must also be relational. It is not something an object possesses on its own, but something that emerges from how it compares to other things. Imagine a universe with only a single object and nothing else. Could it be said to move? There would be no reference point, no external marker to define its position or change in position. In such a scenario, motion loses its meaning entirely. This thought experiment highlights that movement is not about an object traveling through an independent space, but about changes within a network of relationships. This perspective becomes even more striking when we consider light. As discussed earlier, light does not experience time in the usual sense, and its speed remains constant for all observers. If we try to force light into the classical idea of movement, something changing position over time, we run into contradictions. But if we instead think of light as a change in relationships, the picture becomes more coherent. A photon does not move in the way a ball moves. Instead, it represents a connection between two events, emission and absorption. The path we describe is a way of mapping how this connection appears from our perspective. Quantum mechanics pushes this idea further. At a fundamental level, particles are not always well-defined objects with precise positions. They are described by probabilities and interactions. What matters is not where something is in an absolute sense, but how it relates to other systems, how it interacts, how it can be observed, how it influences outcomes. This reinforces the notion that reality is built from relationships rather than independent entities moving through a fixed background. Even space and time themselves may emerge from these relationships. Some modern approaches in theoretical physics suggest that space-time is not fundamental, but arises from deeper connections between quantum states. In this view, what we perceive as movement through space over time is a large-scale pattern emerging from countless underlying interactions. The smooth motion we observe is like a story our minds construct from a more complex relational structure. So when we say that movement might not be about objects changing position, but about relationships evolving, we are shifting from a static, object-centered view of the universe to a dynamic, network-based one. Instead of imagining things traveling across a stage, we begin to see reality as a web of connections that continuously reconfigure. Objects do not carry motion within themselves. Motion appears as the pattern of how their relationships change relative to everything else. This reframing does not deny that motion exists in any practical sense. We still see things move, measure speeds, and predict trajectories, but it suggests that these are surface-level descriptions, useful approximations of a deeper structure where position, distance, and movement are not fundamental ingredients, but emergent features of something more interconnected and subtle. The idea that light behaves as both a particle and a wave is one of the most unsettling discoveries in physics because it refuses to fit into any single category that our intuition can comfortably accept. In classical thinking, waves and particles are completely different kinds of things. A particle is a localized object, something with a definite position, like a grain of sand or a bullet. A wave, on the other hand, is a spread-out disturbance, like ripples on water or sound traveling through air. These two concepts seem mutually exclusive. Something should be one or the other, not both at the same time. Yet light forces us to abandon that distinction. Experiments such as the double-slit experiment reveal behavior that cannot be explained by treating light as just a particle or just a wave. When light passes through two narrow slits, it creates an interference pattern on a screen behind them. A series of bright and dark bands that can only be explained if light behaves like a wave, spreading out and overlapping with itself. But if you try to detect which slit the light goes through, the interference pattern disappears and light behaves like a particle, hitting the screen at specific points. This dual behavior is not just a quirk of measurement. It reflects something deeper about the nature of reality. Light does not switch between being a particle and a wave depending on what it chooses to do. Instead, it exists in a state that cannot be fully described by either concept alone. The wave description captures how light propagates and interferes, while the particle description explains how it interacts and transfers energy in discrete amounts called photons. Both descriptions are necessary, yet neither is complete on its own. This creates a profound challenge for our understanding of movement. If light were purely a particle, we could imagine it traveling along a well-defined path, moving step by step through space. If it were purely a wave, we could think of it as a continuous oscillation spreading through a medium. But being both means that light does not follow a single classical trajectory. Instead, it is described by a probability distribution, a range of possible outcomes that only becomes definite when measured. This idea is formalized within quantum mechanics, where the state of a system is represented by a wave function. The wave function does not tell us exactly where a particle is, but rather the likelihood of finding it in different places. When we observe the system, we do not track a continuous journey. We see a specific outcome emerge from a range of possibilities. This suggests that what we interpret as motion might not be a smooth path through space, but a sequence of probabilistic events connected by underlying rules. For light, this means that its movement is not like a tiny object flying through space along a single line. Instead, it behaves more like a spread-out set of possibilities that evolve and interact until an observation forces a definite result. The interference pattern in the double-slit experiment is a direct manifestation of this. Light explores multiple paths simultaneously, and the pattern we observe is the result of these possibilities combining. This challenges the very idea of a path. In classical motion, a path is something real and continuous, something that exists whether we observe it or not. But for light, the path may not exist in that sense. What exists is a range of potential connections between points. And the active measurement selects one outcome from that range. The journey we imagine may be more of a conceptual tool than a physical reality. This dual nature also connects back to the earlier idea that movement might be about relationships rather than positions. If light is described by probabilities and interactions, then its behavior is fundamentally about how it relates to different possibilities and measurement outcomes. The wave aspect encodes these relationships, while the particle aspect reflects the specific interaction that occurs.